So the next bunch of slides I redid yesterday or someday because a Monday because the slides when I did the morning class they weren't really in an order and people weren't following what we're doing. So hopefully these slides everybody will love better. All right? So the first questions we've been asking right now, is a problem computable, i.e. decidable, which are the same, or not? Right? And we know that the halting problem is not decidable. And then what did we do? We had a whole long list of problems. This is just a subset of the list that we proved were harder than the halting problem. So since they're harder than the halting problem, they're also undecidable. Yes?
Do we have to memorize that list?
I don't know, it's a pretty straightforward list. There's the high problem, there's the halt on the empty problem. I don't know, do you have to memorize it? You should have some flavor for what things are undecidable. All right, so that's what we've done so far, right? So the next thing, what we're going to prove next, is we're going to prove actually the halting problem is at least as hard as these. Right? We're going to do the reduction in the other direction. Not for all of them, but we could do all of them, but we're lazy, we'll just do the high one. Right? So that will prove that the halting problem and these problems are equivalent. That if you can do one, you can do the other, and if you can do the other, you can do one. All right? So we want to prove this, and that's what we're going to do in our next slides. All right? So the other direction, we're going to prove, suppose we already, right, we want to prove that this the halting problem is harder than the high problem. And it's hard to prove that the halting problem is hard. So what we're going to do is we're going to prove that the high problem is relatively easy. We're going to come up with an algorithm for the high problem. All right? So we're going to assume that we have an oracle for the halting problem. And this is kind of what your question is. If you have an oracle for the halting problem, you can do an awfully lot of stuff. And we're going to be talking about that later. One of the things that you can do is solve this problem. Right? And how do you solve it? Well, we're going to build an oracle that solves this high problem. We're given some Turing machine and some input, and we want to know, does this Turing machine ever say hi on this input?
When you see a problem, the halting problem isn't enough proof to say that we had an oracle for the halting problem, we could solve the high problem.
Let's have a new rule that we don't ask questions in the middle of a spiel unless it's related to the spiel. Are you related to this, what I'm saying right now?
Next 30 slides before we just reduce the high problem to the halting problem.
Yes. We did this, and now we're doing this. We proved that this is harder or equal to this. Now we're proving that this is harder or equal to this.
Oh, and since we have
Then they'll be equal. Yes?
By I, you mean every possible integer arbitrary, right?
What?
By I, the input.
I, input. Input is a 0-1 string, probably. All right, so we're given some Turing machine and an input to it. And we want to know, does that Turing machine on this input say hi? All right? So we have to map this over to a different Turing machine. Right? And how do we do it? We just say, well, what does M prime do? It just runs on mi without outputting anything. And then if mi halts, then it prints hi. Right? So what's the point of this? If the oracle says yes, yes, mi halt, yes. No, so we run m on I, and while we're running m on I got it wrong. While we run m on I, if m on I ever says hi, then we stop. All right? If m on I says hi, we stop. Otherwise, we run forever. Right? So if this program halts, why does this program halt? The only reason this program is going to halt is that M said hi. Right? So if he tells us, yes, it halts, then we'll know, yes, M says hi. Yeah?
Is there any situation where it doesn't print hi?
Well, if sometimes M says hi and sometimes it doesn't. If M says hi, then M prime will halt, and the oracle will say yes.
Is this a different flight? Didn't it just say yes?
Yeah, I just changed the slides, right? So if M prime halts, why does M prime halt? Is because M said yes. So if the oracle says that yes, this halts, then we'll know yes, M says hi. But if the oracle says no, it doesn't halt, then we'll know that M never says hi.
And it'll run forever.
Yeah. All right, so that just is proving that these guys are all equal, right? We could do a similar reduction in the other direction. All right? I was just thinking about it over lunch yesterday. It's interesting, proving that this, doing a reduction, that this one is a reduction, but we're not going to do that right now. All right. So now let's consider another funny problem. What's this not problem? This not problem is the problem of, where is it? The not problem is given on M and I. We say yes if M doesn't halt on I, and we say no if M does halt on I. It's just the same. The not halt problem is the same as the halt problem, except we switch the yeses and the nos. All right? And I'm sure everybody's raptured with enthusiasm by this whole topic. All right, so now we want to show that these two problems are equivalent. Well, can we do reduce one from the other? Right? Well, suppose we have an oracle for the not halt problem. We want an oracle for the halt problem. We're given some input. We could give the exact same input there. But now if he says yes, we say no. Right? And if he says no, we say yes. Right? So the question is it fair to switch the yeses and nos? Right? And if we want to prove that a problem is undecidable, then switching the yeses and the nos is reasonable. But if we care about this concept of recognizable, then it's not reasonable. All right? So let's again think about the definition of recognizable. All right? So a problem is computable or decidable if there's a Turing machine that always halts on every input and gives the right answer yes or no. Right? And a problem is recognizable if on the yes if there's a Turing machine, a problem is recognizable if there's a Turing machine which on the yes instances it halts and says yes, and on the no instances it could halt and say no, but it could run forever. All right, so that's recognizable. And let's look at a classic problem, halting. Well, here's an algorithm which will recognize the halting problem. All right, what you do is you just run M on I. And if it halts, say yes. And if it runs forever, then, so run M on I and say yes if it halts. Run forever if no, right? So what does this program do? If M halts, if M halts on I, then this program halts and says yes, right? And if M doesn't halt on I, if it's a no instance, then this probably goes forever, right? There's probably not a space here between for and ever, but I just made the slide yesterday. All right, so the halting problem is recognizable. People buy that? And what's co-recognizable? Problem it's co-recognizable if it's sort of the flip, that on no instances its Turing machine has to halt and answer no, and on yes instances it can run forever. So what? Yeah, so the not halt problem lives up here. All right? Everybody people get these definitions? Any questions? Yeah?
Something is recognizable and unrecognizable.
Sorry, say it again?
Something is recognizable and unrecognizable. Is it computable?
Oh! Give this man a gold star. You always ask very great questions. So, hold that question. I thought it was the next slide, but we're going to just repeat that if we care about yeses recognizable, then you can't switch the yeses and the nos. All right? So what our reduction is, given an algorithm for the right, if we're given an algorithm for the Oracle problem, and we design an algorithm for our problem, then what we do is we do an instance map, and specifically, right, if his answer is yes, our answer is yes. If his answer is no, our answer is no. Right? So that's just, here this is going to say that again, yes goes to yes. That's called a Karp reduction. Both my father and I have written papers with Karp. And I've actually written papers with Cook too. All right, so he's down at U of T. So his reductions is you can flip yeses and nos however you want. What? Cook machine? A Coke machine. I don't know Cook machine. Anyway, we're not doing Cook reductions. All right, we're only doing this yes to yes, no to no reductions. All right, so here was your question. We want to say, suppose we have a language P that's sitting here. It's both recognizable and co-recognizable. All right? So if P can be, accepted and recognizable is the same. If P can be recognized and co-recognized, then it can be decided. Right? And how do we prove that? We just have a little algorithm here. Here's the algorithm given an input which will decide. Right? We have one algorithm that stops and says yes if it's a yes. We have another algorithm that stops and says no if it's a no. So what we do is we run both of those algorithms together, right? And we alternate their steps. And if one halts and gives the right answer, then we halt and give that answer. Right? If the yes guy says yes, we say yes. The no guy says no, we say no. Otherwise, we just keep running them. And we know that either the answer is yes or no, so either the yes or the no will eventually say it. Right? Does that make sense? So that says anything that's in this here comes down here. We're going to watch that little P come down. Ooh. Right? Everybody's kind of follow that? Now, one might ask,
So it's computable.
yeah, if it's here and it's here, then it's here. If it's recognizable and co-recognizable, then it's decidable. So the halting problem. What do we know about the halting problem so far? We know that it's not decidable. We know that it is recognizable. But could it be co-recognizable? Why not? If it was recognizable and co-recognizable, then it would be decidable, right? But it's not decidable, and it is recognizable, so it can't be co-recognizable. Right? Does that make sense? Oh, here we're... Right? So we know that it's recognizable. Suppose it was co-recognizable. Then we just proved it would then be decidable. But it would be computable, right? And those are the same. But it's not, so it's not recognizable. Yes?
That part where you have on top of computable and decidable, you have that part, right? Where it's recognizable and co-recognizable, but not decidable, right?
Here?
Yes.
Yeah.
Are we supposed to have that part or?
No, this part is empty, because if it's here, then it's here. But it's hard to draw these pictures without that there. All right, so now we can do some more reductions, and we show that find some other problems that are harder than the halting problem. Right? If we prove a problem is at least as hard as the halting problem, then what are we saying? We're saying if P has an algorithm, then the halting problem has an algorithm. Right? But the halting problem doesn't have an algorithm, so P doesn't have an algorithm. And in particular, the halting problem doesn't have a deciding algorithm, so P doesn't have a deciding algorithm. Right? Which puts P up there. But also, we know that the halting problem doesn't have a co-accepting algorithm. Right? So P doesn't have a co-accepting algorithm. Right? So that puts P up here. Right? If we know that P is at least as hard as halting, then either P is here or P is up there.
So you're saying how this
Yeah. Now, if we know that P does have an accepting algorithm, but we don't know whether P does, right? So if we also prove that P is less than or equal to the halting problem, right? Then we know that P has an accepting, right? So all those problems, right? These are the problems that we've been looking at here. We proved they're harder than the halting and weaker than halting. And so they all live right in this space. Right? Now, these other problems, now what we want to prove is we're going to look at the first one of these, and we're going to prove, we already proved that they're harder than the halting problem. Right? We did that a while back. This for all one, we're now going to prove that it's harder than the not halting problem. All right? And if they're harder than halting and harder than not halting, then where do they live in this picture? Up at the top, exactly. They all go up there. Into the void. Everybody got that? So, for whatever it's worth, that's what we're going to do now. All right? We're going to prove that this problem, which is given a Turing machine M, does M halt on every input? That's at least as hard as this problem, which given M, we want to know, does it not halt? All right? And the tricky thing is here, we say yes when M halts. And here we say yes when M doesn't halt. So we're flipping halts and not halts, and that makes the reduction kind of hard. How are we doing for time? We have lots of time. Too bad, eh? All right. So let's see what we can do with this reduction here. So we have an oracle that solves the for all inputs problem, and we want an oracle for the oops. This should be M doesn't halt on I. All right. Given M and I, we want to know, does it not halt? All right? So we have to give it some M prime, and it's a little tricky, the M prime, right? Because if if m prime halts on every input, then we want to say, this says yes, so we have to say yes, m does not halt on I. Right? So it's a little tricky. If m prime does halt, then our m doesn't halt. So that's a little hard, and let's see how we're going to do that. We must switch halt to not halt, and here is the algorithm, which is a little funny. All right? So let's see what we're doing here. Given m and I, we build m prime. And what does m prime do is, given its input I prime, what we do is we want to run m on I, right? But if m doesn't halt on I, then m is going to, at some point, has to halt, right? So we can't just run m on I, because if m ran forever, then m prime would run forever, and that would be a problem, right? So we only run m on I for some number of time steps, which is the length of m prime's input. All right? And if during those time steps m halts on I, then what does m prime do on I prime? It doesn't halt. Right? So if m halts here, then m prime doesn't halt. Yeah?
Can you explain again what I prime is? Is that the m that holds an I?
So we're given an m and an I, and we're building an m prime. And m prime takes some input.
Is it arbitrary input?
It takes an arbitrary input.
So then how do you decide what I prime time steps are?
Well, I prime is an input, and when we're given the input, we can see how long I prime is, and we can run m for I time. We can run m on I for that many time steps.
Can I prime be an infinite input?
No, because every input of the Turing machine is given is finite. All right. So let's just look at our cases here. Suppose m and I doesn't halt, right? If an m and I doesn't halt, then this guy, no matter what input you're given, this thing doesn't halt, right? But in this time frame, right? And so m prime halts, right? So that says, for every input, right, no matter what the input is here, if you run m on I for that many m steps, it won't halt in that time frame. So m prime halts, right? So that says that doesn't halt, right? And so that does halt. And so it's saying if m doesn't halt on I, then for every input, m prime halts on I. Right? Are you guys just like, is he still up here talking about this stuff? That's what I'm saying. All right, yes.
Would you be able to go over it again?
Yes.
I think we're just in zombie mode.
We are all in zombie mode. But we are going to survive this course. That's our dedication. All right? We're going to learn enough, and we're going to get through. What do we got left?
We got that final exam.
We got 3 more weeks. But we're going to be in those 3 weeks, we're going to run out of material. So then we're going to have to bring pretzels and have a party. All right?
Oh, no, we're talking.
Now we're talking. All right, so what do we know here? We know that m doesn't halt on I. So now we want to say, given an input I prime, what does m prime do on I prime? Well, what does m prime do on I prime? Well, it runs m on I for some number of time steps. And what do we know about it, what it's doing is M prime is never halts. So M never halts. So M is not going to halt in this time frame, right? And if M doesn't halt in that time frame, right, that's what we say. M doesn't halt, right? So M prime does halt. And so that's what we have, is that if M doesn't halt on I, then for every input, M prime halts on I.
Why is there a not in the circle then? What that mean?
This is just saying, if M doesn't halt, then does M halt? No, M doesn't halt. So we do the else.
Oh, I see.
All right, let's look at the other case. Let's suppose that M does halt on I. Then what do we know? We know there exists some time step at which M halts on I. Right? If it halts at some time. So,
M prime, I prime does not hold.
what?
Wouldn't M prime, I prime does not hold? That. Yes. Yes, wouldn't that be it?
Yeah, well, we were going to say for which I prime. I'm going to come up with some I prime. Right? We have some t at which it halts. Right? There's some t at which it halts. Then let I prime be an input that has length t. Right? I prime is some input that has the right length. And what do we know? We know that M prime on that input runs M on I for that length of time. So the M does halt. Right? So the M does halt. And so for this I prime, M prime doesn't halt. Right? Yeah?
This is clear.
It's clear.
Yeah, but
Are you sure?
one question. You said the other oracle won't run M on M prime, right? It just knows.
Right.
So why are you assuming that run M on I will actually be ran?
Well, this is the same situation. I'm given this input, and I give M prime to the oracle. And the oracle will either say yes or no.
Yes, but why are you assuming that it will read that line? It will read the first line and run the...
This code?
Yeah.
Well, I give the code to the oracle, and the oracle needs to know the answer.
Yes. But for him to know, like, it will give you a yes or no.
Yeah.
Also doesn't help on every input. But you're assuming that it will run M on I for I times the...
No, I'm not assuming the oracle does anything. All I'm assuming is the oracle knows the answer to this problem. The oracle can distinguish. Let's go to the next line.
And the oracle know how many times that you got to run before knowing whether it's out.
The oracle knows. The oracle either says yes, right? I give the oracle M prime, and it can distinguish between for every input M prime halts, or there exists an M prime in which there exists an I prime in which M prime doesn't halt.
How do you determine time step?
We don't have to determine any time step. We have an oracle that distinguishes between these two cases. Right? The oracle, all we know is we give the oracle M prime and it says yes to this and no to this. So what do? We say yes to this and no to this. And that's it. Right? If you believe this case that this algorithm has this property, then we're done. Right? So we have this oracle. We want to do the not halting. Oh, there I have the not halt. Right? Given M and I, we give it this strange algorithm. The algorithm says yes or no. We say yes or no. Right? We must prove it works. If the algorithm doesn't halt, then it says yes. And we Oh, right? If it doesn't halt, then the oracle's, if it doesn't halt, then it's this case, so the oracle's saying yes. We say yes. Right? And if it does halt, then it's the other case, and the oracle says no, and we say no.
So then therefore by Rice's theorem it's undecidable? Or it's unrecognizable? What's your last?
This doesn't have anything to do, we're not using Rice's theorem. This is by, if we had an algorithm for this, we have an algorithm for this. And so what does that tell us? Okay, let's go. That tells us we proved that all these problems are at least as hard as halting before, and just this minute we proved it is at least as hard as not halting. And that proves that they all live up there.
Then we halt we did just before the theorem.
What?
We proved that they were actually equal and in halting, so where are they?
No, so there were other things that were equal. It was a different list. It's a different list that was equal. For example, the exists I that halts is equal. The high problem was equal. These problems all have a feeling that the yeses and nos could be switched to them. All right. 8 after. How are people doing? We live and awake and alert, enthusiastic?
What is that?
When we're done the lecture, you should do like some kind of like mini play to show the oracle, which oracle you're talking about, walk up to it, give an algorithm.
I think you guys should do the play. We'll have an assignment for when we run out of material. We'll have assignments in which people have to come up and do plays, or maybe dance.
We would have to write it out though.
No, maybe dance, or maybe we can do muscle stuff. All right. Let's do another 5-10 minutes of another topic. All right? Whenever you have a class, you can talk about problems being complete for that class. All right? So here's the recognizable class. And what does it mean to be complete for it? It's complete. A problem is complete if it's both in the class, right? So we want it to be living in this circle. And we want it to be sort of at the top of the class, right? We want that for any problem that's in the class, any problem in the class, our hard problem is at least as hard as it, right? So it's at least as hard as every problem in the class, right? So maybe this line should be straight. They're all up here, hard, at the top. All right? So it's the hardest it's one of the hardest recognizable problems. All right? So yeah. Oh, no, we're going to prove that for every recognizable problem it's the hardest. All right? If we had an algorithm for the complete problem, then we would have an algorithm for every problem in the class. You have a question?
Yes. What was the complete problem? Do you have a definition for it?
All right, definition for a complete problem. Good question. So a problem P is complete for a class. It has two properties. One property is it's in the class, and the other problem is it's least as hard as everybody in the class. So for everybody in the class, we prove that the complete problem is at least as hard as it. All right? So what we're going to do now is prove that the halting problem is recognizably complete. All right?
So
Polynomial time?
NP and P is the same or is
So that's a very good question. We're later going to be talking about NP and co-NP and NP complete, and these things are all it's just the same but down. This is whether it's computable and not computable on yes and no answers, and the other one is whether it's computable in poly time or not. It's just moving down the NP world all lives down here. All right, so we already know that halting is recognizable, and now we want, this is kind of, hit him. So he was wanting to know, how does everything relate to the halting problem? You know, how powerful is the halting problem? So what we're going to prove is that for any problem that's recognizable, right, if the problem is recognizable, then there's a Turing machine. What do we know about that Turing machine? On yes instances, it says yes, and on no instances, it might run forever. Right? So what do we know about P? We know about P is that on yes instances, it says yes. Right? So now what we want to prove is that if you can solve the halting problem, then you can solve P. Right? Making the halting problem NP complete. So how do we do this? We want to prove that if you can solve the halting problem, you can solve P. Right? Why is that? Well, if we had an oracle for the halting problem, now we're going to come up with an oracle for P. P is given some input I, and what do we want to know? We want to know, let's take the Turing machine that solves P and change it so that if it ever stops and says no, it runs forever. All right, so now what does P do? Well, if I is in P, then if the answer we require is a yes, then P halts on I. Right? And if the required answer is no, then P doesn't halt. If it halts, then we know I is in P. And if it runs forever, we know that I is not in P. Right? Does that make sense? So that proves that the halting problem is NP complete. Now, remember all of these problems we had before? These were the high problem and the exist problem and stuff. They were equivalent to the halting problem, and so they're all recognizable complete. They're recognizable, and for any problem that's recognizable, halting is at least as hard as them, and they're at least as hard as halting, so they're at least as hard as them. That was the list the list, right? So those problems there. Oh, these problems here, we call them recognizable hard. Why? Because they're harder than everybody that's in recognizable, but they're not in recognizable. Right? They're not recognizable themselves, but for every problem that's recognizable, they're at least as hard as them. And that's all we're going to do today, because we've had enough. Cool. Oh, I just thought of something.